Okay, for this video lecture, I want to introduce you to PyTorch. PyTorch is an open source and free programming library for that's particularly useful for implementing neural networks. So I want to show you some of the features of it and kind of get you started on it. For PyTorch, it doesn't come with Python originally, but you can download it because it's free and open source. And the servers on the student servers at the University of Waterloo, I've asked them to install PyTorch. But for your own machine, you might have to do like a conda install PyTorch, actually conda install torch, or pip install torch. Anyway, you can Google that stuff. So this PyTorch was primarily developed by Facebook, and but now it's basically taken on a life of its own, and it's one of the most common libraries used for neural network programming. So let's jump in. I guess I can say right from the outset, a lot of the automatic differentiation code that I have developed that you've worked with so far is based on the same sort of model, and you'll recognize a lot of the function names actually from PyTorch. Okay, so click here. So first I'm going to read in some standard libraries, but in particular I'm going to import torch. Okay, so now instead of our mat, which is a variable name that I created, or a class type that I created, it's now called tensor. In PyTorch it's called a tensor. So tensor, of course, is a word for like a mathematical array, or sort of table of numbers, and so they use tensor. Here's how you can create a tensor. It's very much like a NumPy array. In fact, it is basically like a NumPy array, except it has the extra little bits for auto differentiation. That's basically what it's about. So here I've created one. You can see for data type, I said the float data type of the torch float data type. I could also have just put a dot in there, and then it would have automatically created a float tensor. You can run functions. There's a whole library of functions in the PyTorch code base, and you can see them all here. So this is pytorch.org. Lots of information here. And right now, I'm looking in the Torch API, and you can see all these different functions: absolute value, arc cosine, and many functions, mul, neg, negative, whatever, all sorts of stuff there. So let's try one. I've already created this tensor up here, x, and I'm going to feed it through the log. There you go. PyTorch has automatic differentiation built in. So let's try that out. Here's this z tensor, and I'm going to feed it through this function called prod, which basically takes a product of all the elements of the tensor. Now, just like we did before, so this y is a scalar function, and I'm going to call backward on it, which is going to feed the gradient down through all of its children nodes. And then so it's going to increment z's gradient, because z was used in producing y. And then we can look at the gradient by looking at z grad. So if y was the z0 times z1, or the two inputs multiplied together, then the derivative, or the gradient, is 2, 1, right? The derivative of y with respect to z0 is 2. The gradient of partial derivative of y with respect to z1 is 1. Okay. So auto differentiation, and the same sort of technique for using that as I implemented in my own mat and mat operations automatic differentiation library. Notice I had to say requires grad equals true. Okay, if you don't do that, it won't offer that function. right? You get this error saying we asked to run the backward thing, but but we didn't say that we wanted to do automatic differentiation. Okay. So you can also temporarily suspend the differentiation. So here's the same calculation as up above. Maybe I want to do something else with z, but I don't want that thing I'm doing to influence the gradient. So I can say with torch no grad, then anything in this block, basically it doesn't increment any of the gradients, or it doesn't add the expression that's constructed in that block to the data structure that implements or updates the gradients. So this basically, it's suspended here. So you can see I used z in y1, and then I used z again in y2, and then I added them together here. But when I actually ran backward and looked at the gradient of z, the gradient pertained to only this part and not this part. Okay, so if I hadn't said no grad, I'll let you do this. If I hadn't said no grad, it would have added these two gradient vectors together, and it would have been 3, 2 would be the answer. So it's pretty easy to convert back and forth between NumPy arrays and torch tensors. So let's take an array and convert it to a tensor. You just use this tensor function here. And there are different versions of this. This is the simplest, but I'll let you discover the alternatives. There are some that are specific to NumPy that duplicate NumPy's type and everything. Anyway, so that works nicely. Now converting a tensor to an array is fairly simple also. To a NumPy array, I mean. You can take your tensor and just say .numpy. Now that works fairly well. A couple of things to keep in mind though. First of all, this NumPy does not make a copy of the memory or of the array. It actually just gives NumPy the data, the pointer to the data, and then you're actually pointing at the same memory location. So you can see I've created the NumPy version here. Now when I change one of the elements of the NumPy version, it actually changes the element in the tensor as well, right? Because this last one I'm printing the tensor, and you can see it's changed the value. So that's something to keep in mind. Another thing to keep in mind is when you want to turn a tensor into a NumPy array, you can run into trouble because there's this all this gradient information, the grad stuff, NumPy can't handle. So if you try to convert a tensor that has a gradient that requires grad equals true, try to convert that to NumPy, it will give you trouble because it says it can't call NumPy on a tensor that requires the gradient. So that won't work. Instead, you have to detach the tensor from the expression graph. So you simply run detach first, and this detaches the tensor from the expression graph so that the grad is no longer there. And that makes sense because NumPy doesn't know what to do with that gradient anyway. Okay, when a tensor is used in multiple calculations, the gradient information is added, just like in when there are multiple paths to a particular variable. You implicitly, well, you don't not implicitly add. The calculus tells us to add those different paths together. This is similar in nature. So let's use z in this product thing again. Now I'm going to say retain graph equals true, saying that I want to add more stuff to the gradient of z, or to the gradients that are involved. I want to add more stuff to the gradients for the things that were involved in this computation. Okay, so z grad is 2, 1 like before. Now I'm going to use z in a different thing. I'm going to say y equals sum. In fact, I could use a different variable here. B. So I'm using z in a different computation, pushing the gradients down through that, and it increments the z's gradient. And so now the resulting gradient that z is storing comes from both of those expressions. A quick joke. Before you criticize someone, walk a mile in their shoes. That way, when you do criticize them, you're a mile away and you have their shoes. So let's look at how PyTorch is used in neural networks. So first, let's look at the data sets. So just like I have a my dataset class and I derive other classes from it to create data sets, PyTorch has, my dataset class is based on PyTorch's dataset class. So I won't go through the details of this implementation, but it's very similar, except it's very similar to my previous classes, except it's based on dataset, PyTorch's dataset class, and it outputs tensors. So for example, when we ask for the inputs, it outputs a torch tensor and targets. And I've also got classes here. You'll see we'll use this later on. So it has two different types of targets. It's got the one-hot targets, and it's also got the class indices. Okay, so let me create a discrete mapping. Plot it. So this is the sort of thing you've seen before. We can look at the inputs. You notice it's a tensor. This is just showing the first 5. And we can get the one-hot targets or the class labels. Now, let's make some neural networks. There are a number of different ways to create a neural network model in PyTorch. And they come from the torch.nn neural network module. So the simplest version is using sequential. So you can see here, I create a torch.nn.sequential object, and inside it's just a bunch of torch layer objects. So here I've got, so linear is basically what my connection layer was. It's basically multiplying by weight matrix and then adding a bias. And then now ReLU is more like a population layer that I had, where all it really does is implements an activation function. So there are lots of different functions. In fact, you can use any of these, I guess. Well, any of the point-based methods. But torch NN. So here's lots of information about PyTorch's neural network library. Linear layers, lots of different layers. Let's see. Nonlinear activations. So softmax, log softmax. There's going to be logistic here somewhere. So lots of things there to look at. So you can create that. More flexibility is offered by the module way of doing it. So you create a class, and I called it mynet, but the class is based on torch.nn.module. In this, in the init, you basically create all the layers that you want. Now, you don't have to do this. Sometimes it's nice to put the layers into a list, just like I did in my own version of the code. However, you don't want to put them in a normal list, because a normal Python list is missing something. I'm not exactly sure what, but somehow it doesn't work. So luckily there's a module list, which after you create the module list, it acts pretty much the same as any other Python list. And then you append the different layers here, and you can, if you don't want to use a bias for a particular layer, just say bias equals false. So this just creates the layers. And now you have to implement the forward method, which takes some input and runs it through all the layers. So since I put everything in a list, I can just go through the list and push my my data through each layer. So once we have that class, we can create an instance of that class or an actual network by just instantiating it. Now we have the network. If we're going to do neural network learning, we're going to need a loss function. So again, this PyTorch web page has lots of loss functions. And I'm going to use the negative log linear loss. It goes together with the log softmax. I'll let you read the documentation on that. Calling the log softmax and the negative log likelihood loss, that combination is the same as cross entropy loss. Anyway, so I've created this loss function. Now I can push my dataset inputs through my network and then compute the loss. Notice the negative log likelihood loss function wants the class index or label indices instead of the one-hot vectors. That's just it's neither here nor there. That's just the way they implemented it. And I can look at this is the output of my network. Now this will be the log of the softmax and the corresponding classes. It's not trained yet, this network. Okay, but that's how you can run the network and compute the losses on it. Now, the connection weights and biases, just like in my classes, in my auto differentiation classes, it creates, a network has a parameters list, if you like. So if you want to see the parameters in the network, you can access them by this net.parameters iterable. So here I'm going through all the parameters, and I'm just going to list what the size of them are. These are all torch tensors. So connection weights. I didn't ask for biases on the first layer, right? So then the connection weights for the next layer, biases for the next layer, connection weights and biases. So if you look at the network design that I had above, you'll see that these are all the right sizes. In kind of an interesting thing to note is that PyTorch has chosen to implement the connection weights as a matrix that left multiplies by a column vector. I've implemented things so that the connection weight matrix right multiplies a row vector. So I implemented row times a matrix, and they're implementing matrix times a column. Doesn't really matter. And you can, if you want to get a list of all the parameters, you can just take the iterable and put it in a list, and then you can look at them however you like. Now, training one of these PyTorch networks, let's look at that. So I'm going to just create my inputs and targets, just read out my data set so it's more convenient. Now here's the learning loop. I'm going to do 200 epochs. I create my network, I've got a learning rate. Now for each epoch I'm going to go through, I do my feed forward pass. I compute the error. Now this losses thing is just so I can plot it afterwards. It's not really part of the loop. I compute the error, and then I'm going to zero out the gradients in my network, and then I'm going to push the gradients down, starting from this expression graph that ended in the error. So this pattern you'll see a lot, except for this line here. So once we've got the gradients, we go through and we basically use those gradients to update the connection weights and biases. So this is where we use torch no grad, because as we're incrementing our connection weights and biases, we don't want to include that. We don't need to track the gradient as we're changing the gradient. So it's usually done in place, and this is basically just gradient descent. This is simple gradient descent. So let's see how this works. So this is loss here on the vertical, and this is epochs on the horizontal. I really should have labeled that. And you can see after I've trained the network, I push the inputs through. This is the log softmax. But if I take e to that, then it gives me the softmax itself. And you can see I get a 1, something close to 1 here, something close to 1, 1, then 1 here. And you can see that it matches the one-hot targets very closely. And if I plot it using my output as the labels, it looks like it's done a good job of classifying. So one last thing, instead of implementing this update myself, this is simple gradient descent, there are other methods that do that step for you. So that's in the optimization module. So in the PyTorch web pages, you can see that over here on the left, optim. And so you can see all the different options. So for example, eta delta is one method, eta grad, and there's a whole bunch of different optimization methods. SGD is one we'll use quite often, stochastic gradient descent. I'll use that right now, actually. So what you do is you give it you basically have to tell it what parameters you want to do the optimization on, and it's going to implement some sort of gradient descent optimization for you. You give it the parameters you want to increment and the learning rate, and some of these optimization methods will want other parameters as well. Okay, so here's my network, then I choose a loss function for it, and then my optimizer. And again, here's this loop. Over epochs, I do the feed forward pass, I compute the error, and then I zero out the gradients. This time I use the optimizer to zero out the gradients. I probably could have said net zero grad as well, like I did before, but I'm not sure, I haven't played with that. Then I push the gradients down, and now instead of that loop where I go through the parameters and I do the gradient increments, instead I just call the optimizer. Oh, I guess I didn't run that one. And then it works. So this is a really quick sort of whirlwind tour of PyTorch and how you can use it to implement neural networks.